Welcome to the second last video in the gravitation topic. In this video we will be looking at Kepler's planetary laws. So Kepler was a German scientist and he lived in the late 1500s and early 1600s. He died about a decade before Newton was born, and his work was the foundation for Newton's law of gravitation. So that is, Newton derived his law of gravitation directly from Kepler's observations and Kepler's work. And that work of Kepler's was his planetary laws. So he came up with 3 laws that describe the motion of planets. And these were, the first law is the law of orbits, and it says that all planets move in elliptical orbits, not circular orbits, with the sun as one focus. Second law is the law of areas, which says that a line connecting the planet to the sun will sweep out equal areas in equal times. And the third law is the law of orbital periods, and that says that the square of the orbital period of any planet is proportional to the cube of the semi-major axis of its orbit. So we'll look at these in a little bit more detail in the next few slides. But first, since we're looking at elliptical orbits now, not circular, it will probably be useful to take a small detour into the geometry of ellipses. So we're quite familiar with circles. A circle is defined by 2 key points, its centre and its radius. The circle itself is the 2-dimensional shape we get if we trace out a line that is equidistant at a distance of the radius from its central point. We also know that a circle has an infinite number of axes of symmetry, and for comparison with the ellipse, I've only drawn 2 of these in. An ellipse is very similar to a circle. However, instead of 1 centre point, we define 2. We call these the foci of the circle, and each individual point is called one focus. I will call the distance from focus 1 F1 and the distance from focus 2 F2. And an ellipse is the shape traced out when the sum of F1 and F2 is kept constant. We can also add in the axes of symmetry in our ellipse. The longer axis, the green one, is called the major axis, and the smaller axis is the minor axis. We also define a property, the eccentricity, which is E, as the distance between a focus and the centre point, where the centre point is the intersection of the 2 axes of symmetry. So in a circle, the eccentricity is equal to 0. Both of the foci are located at the centre point. So in summary, a circle is an ellipse with an eccentricity of 0 and defined by a radius r. The area of the circle is equal to pi times r squared. An ellipse is any shape in which the eccentricity is larger than 0. So when this happens, instead of defining a single radius r, we define a semi-major axis A and a semi-minor axis B, and these are half the long and short axes of symmetry respectively. The area of the ellipse is then equal to pi times A times B. So we can see that actually, although we are much more familiar with a circle is the special case, and the ellipse is the general case. So for a planet to have a perfectly circular orbit around a star, that planet needs to have no forces acting on it except for the gravitational pull of the star. And given that the universe is full of stuff, and all of that stuff has a gravitational force that extends to infinity, that is pretty much an impossibility. For example, in our solar system, each planet has the gravitational forces of all the other planets acting on it at some point. For now, it's important to know that when we're dealing with orbits, we are always dealing with ellipses, as per Kepler's first law. However, in a lot of cases, so for example, for the planets in our solar system, the ellipse is not very extreme. It's very close to a circle. And so in some cases we can approximate it as a circle, which makes the maths easier without distorting the result.